So now we know that for any number, there's a unique representation, there's a unique numeral, base 10. Okay, what we don't know is how to find this unique numeral. Okay. Now let's be honest. Yes, we do know how to do it. You learn how to do it in first, second, third grade, somewhere in there. Okay, but I want you to think about this problem kind of from scratch. Okay, and what I want us to do is kind of to discover how we'll actually find the correct numeral. And the reason I want to do that is because the same technique will work for any base, not just base 10. We're just doing base 10 first because that's our favorite base. Okay, so here's what we have. We have a number n, okay? And n is actually a numbers, okay? And then we have it broken up into a whole bunch of a sub i's. And remember that what we think here is that n is equal to an minus 1, an minus 2, and so on up to a0. Okay, so that this is the numeral. Okay, and what we need to do is we need to find those kind of unique a sub i's that make this happen. Okay, so how do we find them? Okay, the base idea comes from this. Okay, and what we have is that n is equal to this, right? I mean that's what we start with. Okay, and then we'll take out a naught and factor out a 10. Right, this is something that we've done before, right? I mean, this is kind of our usual trick, and that's what we've been using for induction, right? So we take a naught apart, and then what we have is something that looks almost like a numeral, except it's not quite because it starts at 10 instead of starting at 1. So what we do is we factor out the 10, and now we have a numeral because now it starts at 1. Okay, so that's great. And now what can we do? Okay, well, instead of worrying, okay, about the entire list of a's, we're just going to worry about a0. Okay, so this is what we're focusing at. How do we find a0, which is right here? Okay, and as you see from the equation, it looks like n is equal to a0 plus 10 times something. Okay, so what that means is that a0 is actually the remainder of n when you divide it by 10. Okay, and I know that because a0 is a number between 0 and 9 inclusive, right? So if you simply wrote this down and a0 could actually be like 30, right, then it wouldn't be the remainder. But because I know that is less than 10, then it works. Okay, so that really is the remainder. Okay, and we usually write that as n mod 10 or n mod 10 or n% 10, depending on what your favorite language is. Okay, now what we have here, like I said, is n is equal to a naught plus 10 times n1, right? So now the question is, what exactly is n1? And n1, again, because we just did a remainder, what we have is that it must be n divided by 10, okay? And this should be an integer, okay? This is actually the kind of division that we did back in elementary school. So there are no rational numbers. It is simply integers, right? So 7 divided by 3 is 2 with remainder 1. Now just to emphasize this, I'm going to put the floor symbol around it so that we know that that is just an integer. Okay, though it's not necessary from the context. Okay, now what's nice about that is that n1 is now actually equal to the sum from I equals 0 to n minus 1 of a sub I plus 1 times 10 to the I. Okay, so what this means is that I can figure out what n1 is from this formula, and now I have the problem of turning it into digits, right? But notice that I now have a smaller number, right? I started with n digits, and now n plus 1 digits, and now I only have n digits. So recursion seems like a very reasonable plan, right? We're getting an answer because we're going on something smaller. So let's see how we can do it, right? What we want to do is we want to write a program that takes in a number, okay, like say 112, and then produces a list of digits, right? So this should be a list, just like we talked about in the previous unit, right? And it should have numbers in it between 0 and 10, not including 10. We want to do it one digit at a time. We want to discover a0 first. Why? Because our equation gives us A0 first. It gives us the least significant digit. Okay, so that's what we'll start with. We'll start with A0, and then we have a list of digits. Okay, now the only problem is that the least significant digit is supposed to be all the way on the right-hand side, right? So what's actually natural is to compute the list of digits of N1 and then add A0 to the front of that. Okay, so it's actually more natural if we think of a list as giving us the digits backwards. Okay, so here's what we're talking about. Look at numbers to digits of 42, right? Well, here's the answer. Here's the list of 2 and 4 as opposed to 4 and 2. Okay, 2300, 0032. Okay, now I don't want leading zeros, right? But notice that this is not a leading zero. And the reason that it's not a leading zero is because it's actually the rightmost digit. It's the least significant digit, not the most significant digit, which is the first digit. Okay. Now the only other thing that I'm doing that's perhaps not obvious is when I just have the number 0, I want to return nil. Okay. I could actually return a list that contains just 0. That would be reasonable. That would be okay. But the reason I'm not doing that is because I just want to have this fact, okay, this theorem, if you will, that whatever number to digits returns is always a list that does not terminate in a 0. Okay, I was about to say that it doesn't start with a 0, but that's not what I meant. Okay, so that's how I make. I mean, that's what I want. I want to write this program number to digits, and I have here some examples of how it should execute. By the way, a lot of people call this test-driven development. Okay, and what it is, or the highlight of it, is that before we write the function, we write some tests to say what we expect the function to return. And that way, as we write the function, we can actually check that the function is behaving appropriately. All right, let's write this function. Okay, so I'm going to summarize what we know about it using equations. Okay, and the first equation that I have is simply this. The number to digits, abbreviated, and the number to digits of 0 should be nil. Okay, this is something that should be true. Okay, and the other thing that we know that should be true is this kind of recurrent relation, or I should call it the recursive part. Okay, and in fact, the first part I might as well call it the base. Right, and the recursive part is this: if I have n and I want to turn it into digits, then what I'm going to do is I'm going to turn n divided by 10 into digits. Okay, so this is a list, okay, of digits, and then I'll figure out what A0 is, and that's just n mod 10, right? This is just A0. And I'll put that in front of that list. Now, how do I do that? With const, right? Which is our base list operator. So this is something that should be true, okay? And for example, what we're saying is that nd of 125 should be equal to const 5 to nd of 12. I guess I should be consistent on the style that I'm using. So okay, so that's what we want. Okay, that's how we oops, 125. Okay, that's how we're gonna find our digits. Okay, so let's see if we can actually finish this. Okay, so oops, I'm going to translate that directly into ACL2. Okay, so I have two equations, right? I have here equation 1, and I have here equation 2. And equation 1 is what we apply when n is equal to 0. Okay, and equation 2 is when we apply when n is not equal to 0. Okay, so this test here, this is the is n equal to 0 test. Okay, ZP stands for zero predicate. Okay, ZP is dy. It is dy to check whether a number is 0, particularly where we're expecting it to be a natural number. Okay, so ZP of 5 is false. ZP of 1 is false. ZP of 0 is actually true. Okay, and I don't want you to dwell on this, but ZP of anything other than a positive integer is true. That's actually useful because if somebody is foolish enough to type number to digits 10 of pi, okay, then it will actually treat it as 0, okay, and it will simply return nil. And we want that because to generate all the digits in pi would actually take infinitely long, so you never get an answer. Anyway, this is case 1, okay, because n actually is equal to 0, and this is case 2. Okay, so this is the value returned by case 1, and here's the value returned by case 2. Okay, I notice that it is exactly what our formula was. It is cons of n mod 10, right? I mean, this is oh well, never mind, it's right here. Cons of n mod 10, and then number of digits of n divided by 10, floor. Okay, now mod n10, mod ab, right, in more general, is actually the remainder when a is divided by b. So mod n10 is the remainder when n is divided by 10. Floor function, floor AB is actually the quotient when n is divided by b. Okay, so that actually captures this perfectly. Okay, so that's the function. That's all there is to it. Okay, and that should actually convert numbers to base 10 numerals. Okay. Now let's go the other way. I want a function that takes a numeral and goes back to a number. So here are the important equations. If I pass in nil, then it should return 0, right? Because there are no numerals. Otherwise, well, what I have is something that looks like this. It looks like a digit A followed by a list of digits, right? Possibly empty, but it's just a list of digits. So what exactly does that represent? Well, num_L is whatever that list of digits is, right? And what we need to do is we'll take that, multiply by 10, and then add A, right? So what we have is that, for example, num of, say, the list, let's see, 5 to 1, okay? That's equal to 5 plus 10 times num of the list 2, comma 1, okay? And you see that it's actually what I wanted to do, right? Because num of 2, comma 1, actually there's no comma, but num of 2 and 1 will be, okay, 12, okay, if the function works correctly, and multiply that by 10, I get 120, add 5, 125, exactly what num of 5 to 1 should be. Okay, so how do we actually write this function? Well, again, it's not terribly hard. We're just translating these equations. So this is equation 1, this is equation 2. I need one if statement to be able to separate them, and the if statement is right here. Okay, so what I'm checking is L, right, the incoming list, an empty list or not. If it is an empty list, then I'm here, right? This is the empty list case, and remember, const P is true if L is not an empty list. Okay, and then here I am in case 2, and case 2 is just the first element of L, right, which is A, plus 10 times digits the number of everything except the first element of L. Okay, so that should be something that takes a numeral and then returns a number from it.